Thank you for joining us today. We're excited to have you here for the fourth lecture in our TypeDB Fundamentals lecture series. My name is Christoph Dorn. I'm the head of research at Vatical, and I'll be your host and speaker today. Today's lecture will be all about the polymorphic data model, and you will get some detailed insights about how we designed the model and the type system that is powering it. The polymorphic data model implemented by our database TypeDB is a novel data model. It fundamentally re-envisions modern database design by following a highly principled and modular approach that integrates types and polymorphism into the model from the very beginning. And hopefully by the end of this lecture you'll have a much better idea of how this novel approach works. If you attended the previous talks, you'll know that my background is more on the theoretical side. I previously worked as a theoretical computer scientist at Oxford, but I'll do my best not to get too excited by the theory today, and we'll see quite a few practical examples along the way in the lecture. Finally, we're also going to see an in-depth comparison of the polymorphic data model with other prominent data models, and that should give you a very clear idea of where the differences between these models lie. As a brief technical aside, I wanted to mention that there will be a Q&A at the end of this lecture, but you should also feel free to post any questions you may have during the lecture in the chat, and then my colleagues who are watching this will hopefully be able to answer your questions directly. That being said, let's get the lecture started. And since this is, for now, the last of our big 4 fundamentals lectures, I wanted to start us off with a brief overview of the topics that we've covered so far in this series. They'll be useful in giving us a bigger picture and some context for the lecture today as well. In the first lecture, we discussed some of the theoretical motivations of our work, and that started with the observations that databases somewhat lag behind nowadays in providing expressive zero-cost abstractions, which are now found in many modern programming languages and emerging programming languages. These abstractions are, more often than not, built on type systems, because type systems are in a somewhat unique position, bridging high-level expressivity on one side and low-level rigor and mathematical formalization and optimization on the other side. Highly typed languages do often have a somewhat steeper learning curve. You need to familiarize yourself with the type system. Once you reach a good understanding of that, there's almost no overhead in development time anymore. They do force developers to think before they write their applications. That certainly makes applications more robust when written in highly typed languages, and also more composable and more easily maintainable. So all of that is at least well known and common sense in programming language theory, and in the lecture we argued that the same applies to databases, and that type systems and type theory are a very natural modern paradigm for databases, and in particular that types as queries are an ideal paradigm for building a modern query language as well. And finally, of course, type systems are a natural framework for integrating polymorphism, which was one of the goals of the talk, establishing that idea. In the second lecture, we learned from James about some of the more pragmatic pain points complementing the theory. So in particular, James told us about the regular mismatches that we face today between, on one hand, rather aged or domain-specific data modeling paradigms and modern programming language paradigms on the other. So first and foremost, that includes the object-relational mismatch, which is well known and frequently discussed, but James also told us about the object-graph mismatch, the object-document mismatch, and in fact, a range of other pain points, for instance, concerning data integrity or the lack of polymorphic querying that we're facing. There are ideas or there are technologies developed that act as an intermediate layer, wrappers, but these often yield very costly abstractions because we are working with systems that were never designed to really talk to one another. We're faced with non-optimally designed queries and have to keep track of additional object representations and so on. Then finally, in the third lecture, we met TypeDB, the database we're building here at Vatical. TypeDB is a database that builds directly on a novel data model, a polymorphic data model, and is also equipped with a type system. And the type system enables, in particular, an expressive query language that can leverage the inheritance and interface polymorphism in the type system. It also enables very principled database engineering, which by design leads to maintainable and robust applications. And finally, it breaks down complexity. It breaks down complexity because the system is more modular and more composable, and also allows for its components to be continuously modifiable. So all of that is ultimately based on the data model that TypeDB builds on, which is no surprise. The data model is the foundation for building a database. And in today's lecture, we're going to take a deep dive into TypeDB's data model. And I want to touch on 4 points in particular. We'll start with a brief review of some modeling terminology that will be useful for the rest of the talk. We'll learn about concepts, instances, and dependencies between concepts. Then we'll take our deep dive into the data model of TypeDB, the Polymorphic Entity Relation Attribute Model, or PIRA model for short. And we'll try to do that from a more practical perspective and explore the model through TypeQL. We'll also see a comparison of the PIRA model to other existing data models, which I think will be very insightful. And then finally, we'll briefly discuss what lies beyond the data model, which is querying and reasoning with data in a database. And there will be a bit of a preview to what comes maybe in future talks. All right, so to get us started, let's discuss briefly the key terminology in conceptual modeling that we'll be needing throughout this talk. And the first point I want to make here concerns the role of values, of literal values in data models in general. So a literal value is a representation of data that is defined abstractly. So it's defined in an abstract framework, a mathematical framework. It could be numbers, it could be booleans, or it could be strings. Here's an example of a representation of a string. And given that these are abstractly defined, they're not directly useful for real-world applications that work with real-world models. So there needs to be a step that translates the abstract literal value into a more concrete and meaningful concept for the model that we're working with of the real world. So for example, our string here on the slide, QWERTY, could, for instance, be categorized as a plain text password of a user, or it could represent a message between Anna and Bob, or else it could be maybe a keyboard layout in our system. So all of these categories are concepts. So we're talking of a concept of password, a concept of messages, and the concept of keyboard layouts, which provide meaningful ways of categorizing this data, the literal value in the modelers framework. This is a very basic process, but it's still worth giving it a name. So here's a short definition. The process of concept formation is the process of sorting or categorizing data or data structures into meaningful classes, aka types. And for us, this is why types is highlighted here. Types will be the primary terminology, so we will not really speak about classes. We will speak of the type of passwords, sometimes also of the concept of passwords. Term for these categories, for these classes, will be types. And another piece of terminology we need here is the notion of instances. So the data or the data structure that gets categorized, that gets sorted into a type will be referred to as an instance of that type. In fact, values are just one of two kinds of instances and types. And I want to illustrate that with a short example. And I'm going to use a table to organize my data here as an example, but I do want to highlight that tables are a very specific example, and the definitions that we're going to come up with do apply to data models in general. So looking at that table, it's a table titled persons, and it has two columns, name and birthday. And these are the key components that organize our data. So these are the categories for our data, so we can note that down. In this example, we have concepts, i.e. types of persons, we have a concept of names, and we have a concept of birthdays. Two of these types are pretty easy to describe further. So the instances of names are very clearly strings in this example. Anna is a string, Bob is a string, and we could think of many other strings as instances of name. Similarly, birthdays are just dates, so the instances of that concept are, again, values, date values. But what about the concept of person? So maybe we could, as a first guess, say, in our example, persons are just the sum of names and birthdays. That does sound wrong when you say it out loud, and it's even wrong in this tabular example. Indeed, we could simply add another person to this table with exactly the same name and exactly the same birthday. We would still have created a different person. So we've now three persons in our table. So persons are in particular not just the sum of names and birthdays. even going further than that, we could also imagine instantiating a person without any name or birthday. So they don't even need to have names, as long as we have, for example, null as a way to represent the absence of values. So what are persons if they're not the sums of names and birthdays? Well, in this simple example, they're just rows. They're rows in our table. And there's a fundamental difference here between how these rows behave and how the strings and dates behave in the other concepts. Namely, the rows can be made up and constructed freely. There's no limit to the number of persons that we can invent in our model. So while persons as rows are freely constructible, the same does not hold for names. Names are sourced from a predefined mathematical domain. Their instances are strings, and similarly birthdays are collecting values from a predefined mathematical domain, and in that case dates. So one of the types, or two of these types, names and birthdays, collects literal values. The other one collects abstract, freely constructible objects. And this is the distinction that we're trying to make here between the first kind of instances, literal values collected in attribute types, and the second kind of instances, freely constructible objects, where we can just keep inventing new instances, and these will be referred to as object types. There's a third important idea which I wanted to highlight, namely that concepts usually don't exist in isolation, but rather depend on one another. So let's start with the same example that we've just seen of persons organized in a table with names and birthdays. So here we have two persons. One has the name Anna, the other doesn't have a name yet. So what we can do is we can add a name for that person. For instance, let's call them Bob. At this point, all persons in our database do have names, and we can in fact not add further names. And that exhibits a certain dependency between the concepts here. So we cannot create a name without the person that has that name. So because values of names live in rows, there must exist a row for the name to live in. This basic principle of instances of one type requiring existence of instances of another type also appears in many other settings. So let's look at a second example. This is an example with three tables: employees, team, and team membership. And I want to make the additional assumption here that in the team membership table, which has two columns, employee referencing employees and team referencing teams, the foreign keys that reference these different rows in the different tables have to be not null. And what that means is that in order to instantiate a new team membership, and so in order to add a new row in the table, we actually require the existence of an employee, and we require the existence of a team. So in this case, we can add an additional row to the team membership table because we already have an existing employee, Bob, and an existing team, engineer. So again, this is the same principle of concept dependency. We see that creating instances of one concept might be dependent on existence of instances in other concepts. And the general definition here is that of one concept depending on another, and which states that a concept depends on another concept if instantiating the former requires references to instances of the latter. So again, this is something that we're going to see throughout many different examples and many different data models in the talk. Given that this is going to reappear throughout the talk, we will use notation, diagrammatic notation for concept dependency, and we'll use solid arrows to indicate that one concept depends on another concept. Let me add one remark about dependencies, which has to do with different ways of representing these dependencies. Namely, any dependency of a concept on another concept can be, in a refined representation, also be understood as a concept. And in that case, we speak of conceptualizing dependencies. But let's continue with the example that we've just seen of employees, teams, and team memberships. We have seen one way of representing this data, but I want to entertain briefly another way of potentially representing this data. So here's a different schema that could be used. So here we only have two tables, one of employees, one of teams. And in the team table, we have now a column, employees, that's multi-valued. It records multiple employees that are in a given team. In particular, that's somewhat beyond the scope of the relational model, but it's something that could be easily represented in the document model. If we require that each team has an employee, which I want to assume in that second example, then that changes the dependencies of concepts when compared to that first example. Let's draw the dependency hierarchies in both examples. So in the first example, in the first schema, we have these three tables: team membership, employee, and team. And we've already seen that when instantiating team memberships, there has to be an employee and a team that that employee is a member of. So these have to exist in order to instantiate team memberships. In the second example, we have a dependency. We have just two tables, employee and team. And because we record the employees of a team inside the team table and require that each team has employees in it that are members of that team, we have created a dependency of the team concept on the employee concept. These two schemas, or these two ways of structuring your data, are not equivalent. Like, you can express certain things in the first one that you actually can't express in the second. You could still try to represent things with the second schema in some instances. It's still a quite illustrative example because there's a relation between the two. Essentially, passing from the second schema to the first schema turns the dependency into its own concept. So it refines this diagram at the bottom by turning the arrow into its own concept. And as I said, the first schema is a bit more general, it's a bit more refined, but under certain conditions we can also do the inverse transformation to our schema of turning a team membership back into a simple dependency, and we will refer to that process as deconceptualization. So this covers the main terminology that we need for our models and our model investigations going forward. Let's do a brief rundown and a brief summary. So we've learned about concept formation as like a basic mechanism to sort data into meaningful types. We've seen an example where the concepts were persons, names, and birthdays, and that those provided a way of organizing our data. We also learned the difference between object and attribute types. So some types could be freely instantiated. We could just keep making up new instances of them. We could just invent new instances. And person, in our example, was an instance of that, was an example of that. It was an object type. Whereas, for instance, name was an example of an attribute type because we cannot invent new strings. Then we saw that concepts do not exist in isolation. They depend on one another, and we defined that in precise terms. So a concept depending on another concept meant that in order to create instances of the first concept, actually we must reference existing instances of the other concept, i.e. type. Our example here was, again, tabular. We saw that in order to create a new name, in order to insert a new name, there has to be a row for that name to live. So name instances must actually live in a person row. There must be an owner of a name. And finally, as a side remark, we learned about conceptualization as a way of actually refining certain dependencies, turning dependencies into concepts. And we also learned about the inverse process being applicable in specific situations. With this basic terminology settled, let's get into the polymorphic data model. I'm going to talk a little bit about the types and the type system first, and then we'll actually see some practical TypeQL code used to create PR schemas and used to create data instances in PR schemas. But starting from the beginning, introducing the PR model, well, PR stands for Polymorphic Entity Relation Attribute Model. And the model builds very directly on these previous definitions, which I just went through. So the definitions of types concepts, of instances, of dependencies, and of the distinction between values on one hand and objects on the other, or attribute types on one hand, object types on the other. And based on these definitions, the key kinds of types in the PR model very nicely fall into a 2x2 matrix. One of the axes of that matrix is the distinction between types that depend on other types and types that do not depend on other types, so independent types, whereas the other axis is the distinction between object types, so types that can be freely instantiated, so we can create more and more objects in them, and attribute types, so types that can be instantiated with reference to a literal value domain. In the first upper left quadrant, so the independent types which collect objects, we speak of entity types. Then the dependent counterpart we call relation types. And in the case of attribute types, we actually usually want to use attribute types to only refer to the dependent case. There's also the case of independent attribute types, which I'm going to call global constants here. But really, we're going to use those only on one slide going forward. And in general, they're much less common in databases. Yeah. We've seen examples of all of these. So for instance, we saw employees where we could just keep creating employees without any dependencies. We saw a type of team memberships where team memberships needed to be instantiated with reference to employees and teams. So that is in fact a dependent object type. And then we also saw examples of attribute types, like for instance, the name of a person or an employee. It's quite incidental that this 2x2 classification does match very closely with terminology from classical entity relationship modeling. And we do highlight that there is a correspondence by importing that terminology, speaking of entities and relations and attributes. However, it's also important to highlight that for us, this classification fundamentally derives from type-theoretic principles, and that we see this distinction from the perspective of trying to build a very general type system. So let's talk about the type system a little bit. So usually type system comprises two parts, types and type operations that allow us to pass between types. We've already seen the kinds of types that we're gonna have in the prior model, entities, relations, and attribute types. So let's talk about the type operations. There's one fundamental operation in type systems, which is subtyping, which precisely allows us to pass between types by casting from a subtype into a supertype. So a simple example here, for instance, would be considering two types, the type of employee and the type of person, and declaring the former, so declaring employee to be a subtype of person. And that's indicated here in the diagram with a dashed line. So dashed lines will indicate that something can be cast into something else. Well, what does it mean concretely for employees to be castable into persons? Well, it means that if you have an object, an employee object, so an object that's an instance of employee, shown in the upper row here in the graphic, then we can upcast it into a person object. So we can consider that object as a person object. In most programming languages, this casting operation is explicit. In our model here, we don't really care about keeping these castings around. We will usually keep the castings implicit. One also speaks of subsumptive subtyping in that case as a side remark. There's another form of casting, which is also part of the type system, so I briefly wanted to mention it. Very much in a similar vein, for instance, a name Anna in the type name can be also cast into a bare string Anna. There are common operations in our type system that operate on strings, so for instance, string comparison and so on. So by casting the name Anna into the bare string Anna, these string operations then become available. The second example, however, is a bit different from the first example in that it's a system-defined form of casting, whereas the former is an example of user-defined casting. And in fact, there are two different ways a user can define that we can cast objects from one type into the other. The first one is inheritance polymorphism. That's the example that we've just seen. So the Pyrrha model supports inheritance type hierarchies. These can be declared by the user to describe when some concepts, some types are special cases of other types. So for example, we saw employee might be a specialization of person, but we could also declare then special subtypes of employee, for instance, contractor and full-time employee, or further subtypes of person. What we cannot do is we can not declare multiple parent types in the inheritance hierarchies. So this is the first condition you'll meet here. It's a condition of so-called single inheritance, which is enforced by the Pyrrha model, and it means that types can have at most one parent type in the data model. It's a pretty sensible condition to have, so it avoids the so-called diamond problem, which gets much more pronounced in the case of types with dependencies, and it generally also enforces more performant model design. Type checking becomes easier if you only have to walk in one direction in the type hierarchies. The second kind of user-defined casting actually has not to do with types and how these types organize and specialize, but it has to do with dependencies. It's somewhat orthogonal to that first type of casting. In the pair model, we abstract type dependencies. So we abstract them as abstract type capabilities that then can be implemented by other types. Let's illustrate that with an example. So we've already seen how names depend on persons, because names do not exist in isolation. There are persons or maybe other things that have names. And also recall that we use solid arrows to indicate these dependencies. So if we wanted a slightly more general model, we could, for instance, allow names to not only be instantiated with a reference to a person that has that name, but maybe we also want to allow the name to be instantiable with a reference to something else, like a city that also has that name. Now, the diagram is not really reflecting that, because we don't want the name to be instantiated with both a person and a city. We want there to be either a reference to a person or a city that we instantiate the name with. And the canonical way of doing this is precisely to introduce a new abstract type of name owners that name then directly depends on, and to declare that both person and cities can cast into that type. So cities, like persons, can be cast into name owners, and names are now instantiated with such name owners. So both persons and cities have the capability of owning names. The same story, almost verbatim, also applies for relation types. So it was just my personal choice that I started with attribute types here. So for instance, we saw a relation type earlier of team memberships which had to be instantiated with a reference to both an employee and a team that the employee is a member of. And here again, we can introduce abstract interfaces that are then implemented by other types in order to allow various forms of instantiations. So for instance, a team membership could maybe be instantiated not only with an employee, but also an external contributor as a member. So both employee and contributor are then cast into this abstract interface type of members that team membership then depends on. There's also a condition here that I definitely need to mention, which is that in the pair model, we enforce that only object types can be given capabilities. So I've drawn a line here from the name type to the member type. We cannot have that name instances play the role of members and team memberships, because name is precisely not an object type, but an attribute type. This condition too is very reasonable to enforce. It avoids ambiguity that could otherwise arise due to the idempotency of value creation, meaning that if you create a value and then create it later on again, the second operation will not do anything because the two values are the same. In contrast to inheritance, where we had the single inheritance condition, object types can, however, implement many interfaces. So here there are no further condition, and it's actually extremely useful to have this many capability model. In many cases, you can essentially, with a more capability-driven design, express how behavior comes from many different types in your model. All right, so we've seen the types, entities, relations, attribute types, and we've seen the type system, we've seen the basic operation of casting, which had these two different incarnations. On one end, we had inheritance hierarchies, and on the other end, we had interfaces. With the types and type systems out of the way, let's actually dive into the TypeQL practice, and let's see how in TypeQL we can work with the pair model, defining types and defining casting operations. Starting at the top, let's look at entity types. So entity types are, in a way, the easiest types. They're independent types which collect objects. And a new entity type, let's say a new person entity type in TypeQL is defined as follows. So you're looking at a define query indicated by the keyword define. For now, you could think by loose analogy with SQL as this being a create table instruction. And this is followed by person, so that's the type that we want to define here. And then the last part says that a person actually subtypes entity. So what's entity here? Entity is a default abstract supertype of all entity types. So in particular, if a type in our schema does not have a user-defined parent type, then by default it will be a subtype of that abstract supertype entity. And that's very useful. It makes the language in a way more uniform. For instance, if we want to define another type, this time a type that subtypes person, let's say we want to define employee and entity subtyping person, then we would use similar syntax. We would write define employee sub person. Let's draw a little diagram of what we've defined so far. So we've defined two types, the type of employees and the type of persons, and we've also defined this arrow that goes between them that tells us that employees can in fact be cast into person. So this is a case of inheritance, of an inheritance hierarchy. So employee would be a specialization of person. There is the term of abstractness that I definitely need to briefly address. I've mentioned abstractness when I talked about the entity type, the default supertype entity. Abstractness of a type means that no instances of that type can be created directly. So we cannot directly instantiate the type. Any type can be defined abstract. So for instance, we could define person to be an abstract type. Diagrammatically, this would be represented, I would represent that by dashing the border of person. And with person being abstract, we cannot create person objects directly. But they can still be objects in the type by casting. So we can, for instance, still create employees in our schema. We could create an employee object, and that would then cast into the person type. Let's next look at relation types. They're the dependent analogs of entity types, if you want. Let's go ahead and define one. Here I want to define a marriage relation type. The syntax is similar to the case of entity types, so you would start by writing define marriage subrelation. But now, since relation types are dependent types, you also need to specify the interface that they depend on. And recall from our discussion of interface polymorphism that we work with these abstractions of dependencies. So each type carries around its abstract dependencies, if you want. So in the case of marriage, we would define that interface by writing marriage subrelation relates spouse. Diagrammatically, what happened with this declaration is that, well, we created the type of marriage, and we also created the interface type spouse. And at this point, I can tell you that, in fact, we have specialized terminology here. We speak of roles as the interfaces of relations. So we created marriage with a spouse role and a dependency on marriage on spouses. So when we want to instantiate marriages, we now need to make reference to instances of spouses. Then, similar to the case of entities, we can also consider subtypes and organize our relation types into a hierarchy, into inheritance hierarchy. With roles present, there are now different cases how roles can be inherited down that hierarchy, though. And just to briefly cover the basic cases, from which then all other cases can be obtained by combining these basic cases. Let's start with the case of role overwriting. So here in this define clause, we are defining a new subtype of marriage, heteromarriage, and we also are defining what this marriage depends on, which roles it relates. It relates a role of husband and it relates a role of wife. And we specify that these, in fact, overwrite the role spouse. So diagrammatically, what will happen is that, well, first of all, we create the concept heteromarriage. we see there's a way of casting heteromarriage into marriage, so that's a specialization. But then we also created two dependencies here. We created dependencies on the role of wives and the role of husbands. And by specifying that these override spouse, we also allow our wife instances and husband instances to be cast into spouses. So there are now additional arrows relating the wife role and the spouse role, respectively the husband role and the spouse role. Instead of overwriting, we could actually also simply inherit roles. So we could define some subtype of marriage, let's say religious marriage, without touching the spouse role at all. And what that means is that no new roles would be created, so no new interface would be created here, and this new subtype would also directly depend on the spouse role. Somewhat more interesting is case 3 of role extension. So let's consider a subtype of marriage called witness marriage submarriage, which actually introduces a new role. It relates the role of witness, and it makes no mention of that role overwriting spouse. And what that means, so that's the third case here, like in case 2, it inherits the spouse role. So there's a direct dependency arrow from our new type of witness marriage on spouse. But there's also a new dependency on the role of witnesses. And you can see that witness here is disconnected from the rest of the hierarchy. It's not subtyping spouse, for instance. Finally, attribute types. Attribute types are a bit special, again, because they're fundamentally different from entity and relation types in that they collect values. To begin, defining attribute types uses a similar syntax. However, given that they collect values of a specific type, we also need to supply that type. For instance, in order to define a name attribute, which would be a string-valued attribute, we would use the following define query, define name sub-attribute value string. And there are multiple things that happen here. Let's illustrate that with a diagram. So what that define query does is it not only creates the type name, it also implicitly creates an interface for it. And the reason for having this implicit interface is one more condition here in the case of attributes, which is that attributes have a single interface. We also speak of the ownership of an attribute, analogous to speaking of roles in the case of relations. There's a little footnote which explains why it's a good idea to actually have attributes only depend on a single interface, and that has to do with the fact that if attributes had multiple interfaces, then we could also model that using a relation with multiple interfaces and then an attribute that depends on that relation. So there would be some ambiguity here, and the model becomes clearer if we just work with a single ownership interface for each attribute. Given there's only a single one, we can keep it implicit, and we don't need to explicitly provide an identifier, a label for that interface. So here I just came up with one. I'm calling it name owner, and I'll be carrying that around for illustrative purposes. But yeah, it is important that these ownerships are implicit. What about subtyping? As in the case of entities and relation types, you can subtype attributes, you can organize them in inheritance hierarchies. Exactly the same syntax is used. So you would define, for instance, first name as a subtype of name by writing define first name subname. Diagrammatically, what happens here is, well, we get a new type, first name, and that can be cast into names. And what happens to the implicit interface is the canonical thing. So the interface will be a subtype of the unique interface of the supertype. There's one more condition here. So you might have spotted that name now must be abstract. So this is once more special behavior for attributes. Attribute supertypes must be abstract in the Pira model. Again, that has to do with avoiding ambiguity because of the special behavior of values and the idempotent creation. Okay, so we've discussed the key kinds of types and their dependencies. What we have not discussed yet is how to actually implement those interfaces that types depend on. In the case of relation types, that means implementing roles. We also speak of playing roles or being a role player. and it's defined by the following syntax. So for instance, to declare that the type of persons would implement the spouse role of marriages, we would write define person place marriage spouse. Do take note of the scope notation here. So we write marriage : spouse, because usually we don't require role identifiers to be unique globally. We only require them to be unique within a single relation type hierarchy. So within the hierarchy that marriage lives in. And for that reason, we prefix with the relation itself. What happens when we declare that person place the spouse role in the marriage relation? Well, diagrammatically, it's pretty straightforward. We already saw the concept of person, we saw the concept of marriage and the dependency on the spouse interface. So this definition adds one more arrow here. It adds an arrow from person to spouse. And that simply says that persons can be cast into spouses. So they can play the role of spouses. Yeah, they can be cast into that interface type. Let's extend the example a little bit. So the diagram I'm drawing here is simply what we've just defined. Let's extend it a little bit just to play around with the types of constructs of schema definitions that you can do. Let's look at the diagram. So we define a subtype of person, civil servants. We define a new relation of registry entries. That relation has two dependencies. It depends on the role of events and depends on the role of registrars. So in other words, a registry entry needs to be instantiated with an event that is being registered and the registrar that is registering that event. And we also define in the define clause that marriage implements the event role, it plays the event role, and civil servant plays the role of being a registrar. So what can we infer from looking at that diagram? Well, importantly, we can infer that civil servants can be cast into persons, given that they're subtypes, and then persons can be cast into spouses. So that means civil servants too can be cast into spouses. So the capability of persons playing the role of spouses is something that is inherited automatically through to civil servants. In contrast, civil servants, which are specialization of the person type, they do play the role of registrar, and that is not played by general persons. So you can't easily downcast persons in general to civil servants. Not all persons are civil servants. Implementing ownerships is the analog of implementing roles for attributes. So let's also briefly look at that. Again, it's object types that can implement ownerships, and this is declared using the own keyword. We also say that a type owns an attribute. So we would write define person owns name. And what that would mean, very similarly to the previous slide, it would mean that we add an additional arrow to our previous definitions, an arrow from persons casting into name owners, meaning that persons can now be cast into name owners, and that means in particular names can be instantiated with persons, with a reference to persons. This similarly works for relation types. These two are object types, so for instance we could imagine another attribute of dates depending on an abstract ownership, depending on date owners, and then we could declare that marriage owns date, and that would entail that now marriages can be cast into date owners, into the role of date owners. And as before, as we've illustrated in the previous diagram, these capabilities are inherited through inheritance hierarchies. This completes our schema definition section of the prayer model, but of course the type schema, so the definition of types and the definition of how we can cast between types is just one part of the database. The other part is data instances. And what I want to do here is I want to take the schema that we've assembled, which is shown on the right, and I want to start inserting some data into it. So the schema on the right is really the amalgamation of different definitions that we've seen before. We've seen all of these definitions though. So we have a person type. Person type implements the name owner interface. So it owns names, persons own names. Person also plays the role of spouse. Marriages depend on spouses, so they need to be instantiated with spouses as a reference. Marriages are date owners. They can be cast into date owners on which the date attribute depends. And then there's also the relation of registry entries depending on the event role and the register role, which in turn is played by civil servants, subtyping persons. So it's really just taking all these different examples that we've seen before and combining them into a single schema. In TypeQL, you would now insert data into this with a insert query. So that starts with the keyword insert and then inserts data, so values and objects into these individual types, very much following the principles that we've discussed. So nothing should really surprise you, but I'm still going to go through this insertion clause step by step and explain what happens in the background under the hood when you run this insert query. So let's look at the first line. A is a civil servant. As you can probably guess, what this is doing is it's creating a new civil servant object. We check civil servant as an entity type, so it collects objects. We can simply create a new civil servant object. And I'm illustrating that with this new civil servant syntax, which is not TypeQL syntax. It's only here for illustrative purposes. Once we instantiated that new object, we then assign it to the variable $a. In the next line, we are dealing with values. So what we want to do here is we want to add the value. We want to add the value Anna to our type name. But recall that names are dependent types, so they depend on name owners. They need to be instantiated with a reference to a name owner. This reference is what we refer to here as a having the name. So that means that Anna is instantiated with a as the object being the name owner. We can look at our schema to see whether this type checks. And indeed, civil servants can be cast into persons, which can be cast into name owners. So it's a valid name owner. The next lines are pretty similar to the first two lines. So in this case, we are creating a new person object. $b is a person. And in fact, here you see the comma notation, the comma syntax of TypeQL in action. So if you have two statements with the same subject, then you can contract them with a comma. So really the full statement here would read $b1 is a person, $b1 has name Bob, but we're contracting it into $b1 is a person, has name Bob. What happens under the hood? Well, very similar to the first case. We first create a new person. Again, that's easy and straightforward because it's an entity type. We can just create a new person without having to reference any other object. Then we assign that person to the variable b1. Then we want to create a new name. We want to add the name Bob. But again, we need a reference to a name owner. In this case, the name owner is going to be the object stored in the variable b1. So we say that b1 has name Bob. Exactly the same happens in the following two lines. Importantly, we create a new person, so a second person with the same name. And this still is an operation that does something. The name Bob is the same as before, but it has this time a different reference to the name owner. So it creates a different reference of name ownership, in this case to the variable, to the object stored in the variable $b2. If we were to run the same statement again at this point, so if we would write $b1 is a person, has name Bob again, this in contrast would not do anything. So this is where the idempotency of value creation comes in. So it would be the same reference to an object from the same name, and this already exists in our database. The next line is a bit more interesting now. Here we want to create a marriage object. Maybe you can focus on the is a marriage part first. So that tries to create a new marriage object and then assigns it to the variable $m. But looking at the schema again, marriage is in fact a dependent type. So unlike the case of persons and civil servants, we can't just go ahead and create a marriage object freely. We must reference instances, existing instances of spouses. And that's achieved by the tuple notation that provides a tuple of spouse role players here. So we have the spouse b1 and the spouse b2, which means that these two objects are referenced as spouses for the creation of this new marriage object. The next line, again, something that we've hopefully now understood, creates a new attribute. It creates a date attribute. Date itself is dependent. It needs to be instantiated with a date owner, with a reference to a date owner, and the reference is made to M being that owner, so M has the date. Final line instantiates another relation. So this time we instantiate the registry entry relation type. This works very similar to the case of marriages. It's interesting in that in this case we don't assign the newly created object to any variable. So this is completely fine as well. We can create a new registry entry. The only thing we need to do is we need to reference an event that's being registered, and we need to reference the registrar that performs the registration. We can do that. We have a civil servant object stored in our variable A, so that can be our registrar, and we have a marriage object stored in the variable M, and that can be cast into the event that we need to reference. So this creates a new registry entry object, and it does not assign it to any variable, which is a completely fine thing to do if you do not require that object to be used in later statements. So this is a pretty extensive look at data insertion in the Pira model. Hopefully it demonstrates that fundamentally it's very easy. So there's this basic distinction of things that depend on other things, and this basic distinction of creating values, which is idempotent, and creating objects, which is not idempotent. You can just freely invent new objects, but that's it really. So this is all you need to know to understand how data instances are created in the Pira model. There's a little bit of fine prints, given that this is meant to be a comprehensive overview of the Pira model. I wanted to at least briefly mention the following more detailed points. The first concerns the veridicity of roles. So we've seen in our schema that we actually defined marriage with a single role. We defined marriage subrelation and only stated it relates spouse. But then when it came to data insertion, we actually inserted marriage with two references to spouses. So we had two spouse role players, B1 and B2. And indeed, the number of spouses here can be variadic. There can be any number of spouses. In this case, there should be at least one spouse. You cannot instantiate a marriage without any references. After all, it is a dependent type. But apart from that, there can be any number of spouses. And this veridicity is very useful in many modeling scenarios. It's also very lenient, and often you want slightly tighter constraints on cardinality of roles, which is something that is part of the formal Pira model and which is going to be addressed in slightly more concrete terms as well in upcoming versions of TypeQL. The next point concerns the globality of attributes. As it turns out, I actually lied to you when I said that attribute types have to be instantiated with an owner. They can also be instantiated without an owner. So for instance, the following is valid TypeQL. You can write insert Chloe is a name. And what that would do under the hood is, well, it would also add Chloe, the literal value Chloe, to the name type, but it would not give that value any owner. And this is precisely what we referred to earlier as a global constant then. It's not something that probably many of us will use on a daily basis, but in this sense, all four quadrants of the 2x2 matrix that we saw earlier are represented in the Pira model. And then finally, technical remark about a condition that actually affects data instances. We've seen a range of conditions that concern the types and the type systems. Here's one condition that affects how you can insert data. And that condition says that if you want to instantiate a dependent type with a reference, then that object that is being referenced has to directly play the role or has to directly implement the ownership necessary. And directly here means without passing through sub-interfaces, so without passing through sub-roles or sub-ownerships. And just to illustrate this, it sounds like a more technical condition, but really it comes down to a sort of diamond problem again. So if you have, for instance, a schema of an ownership relation that relates an owner, and then you subtype that owner role into subroles, car owner and play owner, and then you actually declare that only these subroles, car owner and play owner, are played by, let's say, an entity type adult. Then if you were to instantiate an ownership with reference to an adult object, it would be ambiguous whether you meant a car ownership or a plane ownership, whether you wanted the adult to play a car owner or a plane owner in this relation. Let's actually focus on the main aspects that we've seen in the section. So we've learned about the three main kinds of the model. We've learned about entity types, we've learned about relation types, we've learned about attribute types. We've also learned that these type kinds are organized into inheritance hierarchies. So, for instance, we saw the example of employee subtyping person. We saw a different form of casting by interfaces. So all dependencies were abstracted by interface types. That meant that all dependent types depended on abstract types, like, for instance, names could be instantiated with name owners instead of like a specific type like person. We learned that object types can implement these interfaces, object types and only object types. So for instance, we could have persons implementing the name owner type interface and city implementing the name owner type interface as well. And that means that name can be now instantiated both with persons as owners and cities as owners. As a condition on these polymorphic casting operations, we've learned that we work with inheritance in a single inheritance system, so there can only be one parent type, but interfaces can be implemented in various ways. So there's a multi-capability model here, where types can have multiple different capabilities. They can implement multiple different interfaces. We've also talked about data instances, and there were no surprises there. We saw how to create object types, which was very straightforward, and we also saw how to create value types. We saw how to deal with dependencies properly, and we understood what was really happening under the hood when we instantiated dependent types. This was really a pretty in-depth view on the Pyro model, so if you, after the talk, go back to some sections which we glossed over a bit too quickly and just recap the details of what we covered here, I think you'll find that we covered a substantial part of the model, and if you understand everything covered here, I think you're really well set up to work in the Pyro model. Let's now go on to a comparison with other models, and I want to start with a somewhat reversed order of events here, and I want to start with the bottom line, which connects to maybe this last slide of the Pyro model as well. So what we've just seen is that really the Pyro model is a very principled and ultimately also a very simple model. So the ideas, the fundamental ideas are here very simple, and these fundamental ideas are found across essentially all data models. And as a result of this, from the perspective of the Pyro model, capturing the other data models is actually pretty easy. And I now want to substantiate that bottom line. I want to substantiate that claim by going through a range of data models, a selection of data models, in each case deconstructing the data model into these fundamental ideas of types and instances, and then comparing it to the Pyro model. The first model is the relational model, the first model that we'll compare the Pyro model to. We've already seen examples of the relational model floating around on earlier slides, so this shouldn't be too difficult. In particular, we've learned that there are two ways of organizing data, of categorizing data in the relational model. First of all, data is categorized by table, and the instances of different tables are rows. And then secondly, data is categorized by column. And there's a distinction here that we should make between, on one hand, columns that hold values. So for instance, the column name holds simply a string value, in which case the instance is a value, an instance of an abstract value type. And then there's another case of columns, which is columns that hold references to other rows. So I'm referring to them here as foreign key columns. So really, often these references are encoded by values themselves. I'm somewhat abstracting the model here a little bit and want to instead think of these columns holding objects that really just comprise a pointer to a row in a foreign table. In that sense, these foreign key columns have reference objects as instances. And in particular, I also want to identify IDs of a row with the row itself. After all, these are in one-to-one correspondence. Let's look at the dependencies between these concepts. So that's also pretty straightforward. We've seen that columns, for instance, a name column, is contained in a table. So there's actually no way to instantiate it without reference to a row. So columns depend on the tables they're contained in, and there's another dependency of foreign keys on the objects that they reference, because of course these need to exist before we can instantiate the foreign key. Maybe as a small remark, we've also seen constraints earlier. For instance, we've seen not null constraints in foreign key columns, and such constraints can modify dependencies. But they modify dependencies in an obvious way, which very much still fits in the same picture. So it will not be super relevant for the discussion here and can be very easily incorporated as well. With the types and instances defined, let's look at a simple example of the relational model. So let's look at a two-table example, a variation of example that we've seen earlier. So we have employees on one hand and then a table of teams on the other. Employees have now not only names, but they also have a foreign key column which references a row in the team table. Whereas team, besides the ID column, which we however identify with the row itself, only has a team name column. So what would be the para analog here? Well, it's the as a first step, let's extract the types, and the types are the table concepts, so data categorized in tables, and the column concepts. So in this example, for instance, we have tables of employees, we have the table of team, we have columns of name, we have another column of team name, both of these are value columns, and then we also have the foreign key column member of. As explained by the previous graphic, these have various dependencies. In particular, the columns depend on the tables that are contained in, but also the foreign key column now depends on the table that it references. So the dependency graph would look something like this. Is this the PR schema that would correspond to our simple example? It's not yet the exact PR schema, because indeed, if you remember, in the PR model, we abstract all dependencies. So really what we still need to do is insert the interfaces that abstract these dependencies. So for instance, instead of having name directly depend on employee, we introduce an interface and ownership of names as a type in between that employees can then cast into. And with this modification, we would then arrive at the PR analog of our simple relational example. At this point, I want to introduce a small convention, namely, so far I've always carried around the ownerships of attributes. Given that these ownerships are uniquely associated to the attributes, that's of course not strictly necessary, even though it's illustrative. It's illustrative to think about an employee casting into a name owner that a name can then depend on. But usually we actually do not draw this interface. So from now on, I want to replace the dependencies on attributes on their ownerships, and then the implementation of those ownerships by a single arrow that will be labeled with owns. So for instance, in our example here, we would have a single owns arrow from employee to name and a single owns arrow from team to team name. And then similarly, we are annotating the other arrows with the corresponding TypeQL keywords. All right, that was simple enough. Let's look at another example. Let's take the graph model, by which I really mean the labeled property graph model. First and foremost, the graph model comprises nodes and edges, and both of these are categorized. So nodes are categorized by labels, so-called node labels, and edges are categorized by edge labels. There's also values, of course, in the graph model. Every data model has a value somewhere, and these values are categorized by property keys. These property keys are in fact contained in nodes and labels, so that creates a dependency. And edges also have an additional dependency. Edges depend on nodes because edges cannot be instantiated without pre-existing nodes that the edge should run between. So these are the dependencies that we have in the model. Edges must refer to existing instances of nodes, their start node and their end node, and property keys are contained in edges and nodes, so they're associated to existing instances of edges or nodes. Yeah. Also want to add a small remark here about a detail that I'll be glossing over, which is that in the labeled property graph model, nodes and edges can also be assigned multiple labels, which sort of emulates subtype hierarchies or nodes having multiple types. However, there's no really meaningful way to model inheritance with those multiple labels, which makes it less interesting from a type system perspective. Just as in the relational example, we've now seen our types and instances. Let's look at a concrete example. Here's a very simple graph database. So we only have 3 nodes, 2 of which are labeled with employees. So they're categorized in the employee type, and one of them is a team node. And then there are also edges between them. These are labeled by member of. So employees are here a member of teams. And then there are various property keys. So for instance, employees have a name key, which points to the name of that employee node. And members have a position key, which holds the position, is a string value describing the position that an employee has in a specific team. And then team nodes have a property key, team name. So just as in the relational case, it's pretty straightforward to extract the types here. So we have, just as before, we have employees, teams, names, team names, and a member of label for edges. Now we also have one more additional concept. We have the concept of positions. The dependencies, again, we already explained those in the previous slide, also pretty straightforward. So property keys are associated to specific edges and nodes. So for example, the name concept depends on employees. The team name concept in this example depends on teams. Positions, in turn, are actually keys that we give edges in our example, so they depend on the edge concept of memberships, of member of. And then, of course, edges themselves also have dependencies. In this case, in our example, we can reverse engineer from the database that member of actually depends on both employees and teams. These edges should run between employees and teams. Once more, this is not yet the schema that we would build in DB for the peer model, because we still need to introduce the interfaces here. But once we introduce the interfaces, we're done with our migration from the graph database, which in this case was also pretty straightforward. Let's look at one final example, which will be the document model, and let's do the same exercise again. The document model is a bit more interesting. So the document model, in effect, has only 2 ways of talking about categories of data. So the first one is pretty easy. We have documents, and these are organized in collections. So they're categorized by collections. So here, collections are our types. But then the second kind of type is keys. And keys are interesting because we really need to make a distinction of what the key holds. So for instance, the key could hold a subdocument, in which case the instance of that concept would be an entire document. The key could also hold an object ID pointing to a document in a collection. Just as in the relational model, we're going to abstract that a little bit and then think of these instances of these keys to foreign object IDs as references, as reference objects. And finally, it could also be a simple key that just holds a value. So for instance, it could just be a name key that holds some string value. And that's the third case of instances that a key can hold. Let's look at the dependencies. Well, it's pretty straightforward. Keys have to live inside documents. So the document better exists before you generate the key. So there's the dependencies of key on documents as instances of collections, or maybe as subdocument instances of keys. And there's also dependency of keys that hold references to other documents for those documents to exist. So before you can instantiate that reference, that other document needs to exist. So there's a dependency between keys to foreign IDs on documents and collections. As an aside, the document model can get even more confusing for the semantic modeler, because often there are duplicates of data, like we're embedding data in multiple places across our database, and there's no real way of keeping track that these represent semantically related entities, they're logically independent. So that complicates the semantic modeling part, but here we are only thinking about logical dependencies, so we'll gloss over that detail. And finally, an example for the document database. So here we have a document database with two collections, a collection of employees and teams. I've inserted two documents in the employee collection. So we have a document with a key name, and that holds a name value, it holds a string. For the first document, that's Anna. For the second document, that's Bob. And then we have a single document created here in the team collection, which looks a bit more complicated. So first of all, it has a key to a value, team name. So that holds a string value indicating the name of the team. And then it has a key, members, which actually holds a list of subdocuments. So the instances of that key are documents themselves. And in each of these subdocuments, we again have keys. We have one key pos, so abbreviating position, which just holds a value, a string value indicating the position of that member in the team. And then we also have another key, EID, employee ID, that references a document in our employee collection. So what are the concepts? What are the types? Well, everything I've just listed. We again have teams, employees, names, employee IDs, members, team names, and positions, with the various dependencies that we've just discussed. So, for example, there can be no position without a member in a team. So member is, in fact, a key that lives inside members document describing one of the members. Similarly, there can be no name without first creating an employee document for that employee to have the name. So there's a dependency of name on employee, and so on. What's interesting in this example is the case of employee ID. So employee ID, based on the explanation on the previous slide, well, it's contained in the document of members. So it depends on a member, first of all. It's the employee ID of that member. And then it also references an employee. So the employee document that it references must exist. So there's a dependency on employees. We could go ahead and transform this into a pure schema. But it's also an interesting example of a schema modification that we can often do and that we've seen at the beginning of this talk. Namely, with the additional constraint that actually every member in a team, so every of these member documents, should definitely have an EID. If that's the case, if all our members have EIDs, employee IDs, then we can also go ahead and deconceptualize the EID relation and instead think of members as having a direct dependency on the employee, as having a direct reference to the employee that they record the membership of. So this is an example of how you can frequently modify schemas, like turning dependencies into concepts and turning concepts back into dependencies. And in fact, by doing this modification, we've now arrived at the same schema that we, for instance, saw in the graph example. So this is exactly the same schema now that we come up with in the graph example. Okay, so what do we see? We disassembled three prominent data models into their basic ingredients. We thought hard about what are the concepts that really categorize data in these models, how do these concepts depend on one another, and well, the three diagrams on the left summarize what we found. And what I think is quite curious is that despite the details being quite different, there's certainly some pattern here. So there's certainly some similarities in the pictures that we've drawn. Of course, if you look closely, there are also many ways in which these models differ. The Pira model somehow crystallizes this picture in a more principled and in a more unified way. So in the Pira model, in contrast to the three models on the left, we have our three types that we've seen: entity types, relation types, and attribute types, clearly distinguished by the left two being the object types, and the right two, so relation types and attribute types, being the dependent types. Now, dependencies of these types are not direct on other types. Instead, they are modularized. So these dependencies, as we saw in our discussion of the Pira model, are in fact on abstract interfaces. And these interfaces are then implemented by object types. And finally, a feature that does not come up in any of the models is, of course, inheritance. So in subtype inheritance, organizing our types in inheritance hierarchies. If I were to summarize these three models and how they compare to the Pira model, I would probably say that principled, modular, and polymorphic is pretty much what sums up the Pira model. So it's much more principled in the way it organizes the types. It's modular in how it deals with how data depends on other data, and it's also polymorphic in having both interface polymorphism for implementing dependencies and inheritance polymorphism for organizing the types that you work with in your schema. To summarize, well, in comparison to these other models, we've seen Pira model is principled. We have explicit and unambiguous functions of our types. It's more modular. We can very safely modify implementations without breaking dependencies, and that makes the model much more flexible. We can have name owners that reference either cities or persons, and we can change these implementations independently of the dependencies of name owners. And we have polymorphism expressed both through type capabilities, i.e. interfaces, and type inheritance. There's more in terms of, for instance, variodicity, globality, which are all things that we talked about that just mean that there are less restrictions imposed on how we can organize our data. A final point I want to make here in this comparison is it's definitely worth highlighting the Pira model compared to these other approaches as a types-first approach. In fact, in the more schemaless approaches, we kind of extracted types as an afterthought. So types don't really feature as first-class citizens. There's no a priori type system that is being used. Instead, in the Pira model, we need to think about types ahead of time, which you could think is pretty painful, but actually a lot of the pain is taken away by this more modular approach of the model. All right. Very briefly, let me also discuss what comes after the data model. So of course, now we've learned how to build our database schema. We've learned how to insert data into our database. But that's just one part of the equation of building a database. The other is, of course, querying. And in our case, it's also reasoning. And both of these are very tightly intertwined with the Pira model because they're based on the idea of patterns. So that's essentially the root of type-theoretic querying. So queries in the Pira model are based on patterns. And by patterns, I really mean types. So that's the types as queries paradigm in which we define a data type of solutions in order to describe the data that we want to retrieve from our database, which naturally leads to a fully declarative query language. This sounds a bit abstract, but it turns out to be very intuitive. So I want to at least show one or two examples of patterns here and how they can be used in querying. And then there's also the type-theoretic reasoning part, again based on patterns and very naturally part of a type-first approach. After all, a type system is just a collection of rules. So for instance, subtyping says that, well, if one type is a subtype of another type, then an instance of the subtype is also an instance of the supertype. And very similarly, we can allow user-defined rules that in a way extend the type system by deriving new instances from existing instances. So that is also a very natural part of this type-theoretic approach to databases. So to summarize, both are key functions of the Pira model. They're large topics, so they definitely deserve their own discussion. And here I just want to give a very brief preview of them. Let's start with the pattern-based querying, and particularly I want to illustrate interface polymorphism. What you're seeing is the anatomy of a query in TypeQL. There are new keywords that we haven't seen before. There's match and fetch. So the match part holds the pattern. So the pattern is just a collection of statements with variables that can be solved for by substituting these variables with either objects or attributes. And then the fetch clause is a way of formatting these solutions in a human-readable format, in this case in JSON format. Let's go through this line by line. So let's look at the first line in the fetch clause just to get a bit of familiarity with the pattern-based approach to querying here. So I also want to remark that all of these terms that you're seeing here, you have seen already when we discussed data instances. So this is really how we use type statements to build complex constraints for data to be retrieved from the database. But yes, let's look at the first line. So it starts with $eng_team is a team. And what that does is, well, it assigns to eng_team some existing team object. So some already existing team object is now eng_team, but it could be any at this point. And then the line continues with has team name engineering. So this now means that eng_team, in fact, must have the team name engineering. So there must be an attribute engineering in our database with reference to eng_team, the eng_team object as its owner. Then in the second line, we, ignoring the tuple, the bracketed tuple for a moment, we state the existence of a team membership. So we say there is a team membership, but we leave that unassigned. We don't assign that to any variable. What we do require is that this team membership actually has specific role players. It has the role player eng_team, which was a variable that we used in the first line of the match clause, and then it also has a member role player m. So this is a new variable introduced in that line. So what does that object stored in the variable $m now represent? Which concept does it belong to? Well, the answer is in a way polymorphic, because the only thing we know is that m now belongs to data in some type that implements the member role, that plays the member role. So in this sense, we can query many types, potentially many types at the same time, as long as these types implement the member role. And then the fetch clause is only interested in the variable $m, so it fetches m as an engineer and returns for each of our engineers the name. Let's look at a second example briefly, which connects back to our discussion of inheritance polymorphism. So the schema at the bottom extends our previous schema a little bit. So instead of just employees which play the role of members and team memberships, let's assume there are some special subtypes of employees, like directors, maybe contractors. And our director subtype will play a specialized form of membership role. It will play the role of leader in a team leadership. Now let's consider the pattern that we have in our query. So this pattern starts off with saying that E is any existing employee object. So in particular, E could be a director object because directors can cast into employees in our schema. But then the second line actually states that E is a leader. E plays the role of a leader in an existing team leadership. How can that be? I mean, after all, we initialized E as an employee object. Well, because E can in particular be a director object, the type checking still works out here. In fact, we can infer that E must be a director because only a director plays the role of a team leader in our schema. And then finally, as before, we have the fetch clause, which nicely formats the answers that we're interested in. The same simple syntax, so the same pattern-based syntax also applies to rules. And this is going to be my only example of a rule, but I feel like it nicely illustrates the point. So a rule consists of a when clause, and that contains the pattern stating the rule's assumptions. So it defines constraints that variables need to satisfy. And then it has a then clause which tells us which data can be derived. So going through this rule here, the when clause states that when D is any director object and D is also a member, it plays the member role in a team, then, this is now the then clause, D is in fact the leader of that team. So in other words, this rule simply states that when we have directors which are members of a team, then we think of them as leaders as well. And once more, one of the main points I want to illustrate here is that all of this uses the same syntax that we've already seen in our data insertion and schema definition language. So it's based on the same ideas of the type system, of instances, and of dependencies between types. So to summarize, patterns are a natural part of the Pyra model. They just express combined statements about type instances and dependencies. They're fully composable. You can compose them in any way, and they're fully declarative. And importantly, they can also be type checked to catch errors before they happen. And they underlie the two key functions of the Pyra model that are core parts of TypeDB. They underlie the type theoretic query language, and they underlie a rule-based reasoning engine. Once more, this was a look ahead, so do stay tuned for more in-depth content on our type theoretic query language and on our rule-based reasoning engine. For now, let's review what we've seen in this rather long lecture. Well, we've had an in-depth view of the Pyra model, which, as I should say, is a fast-evolving model for modern databases, but we hope it will play the role of a very foundational contribution to the data model space. These are my two favorite graphics from the talk. So on one end, we had this nice 2x2 classification of types, which rooted in the distinction of independent types and dependent types, and of object types and attribute types on the other hand. And then we also had a nice graphic that organized the different types in our type system, how these types can be cast into each other through interface implementations and through inheritance subtypes, and also how these types depend on one another. And what we've done is, well, we've defined some core ideas of conceptual modeling that enable this classification, and using those core definitions, we've in essence re-derived the Pyra model from first principles. And of course, we've also then compared the Pyra model with other data models. We've reverse engineered the types and the type dependencies of these existing data models. And what I want you to take away from this lecture is that in comparison with these other models, the Pyra model is certainly a much more principled, modular, and in particular polymorphic approach to data modeling, and as a types-first model. And as a topic of future lectures, it comes with a beautiful query language, TypeQL. It's easy to get started with TypeQL. And it has a powerful reasoning engine that breaks down very complex application logic in a set of simple rules. Thank you very much for staying with me through this lecture. Do check out our previous lectures, which are available to watch under typedb.com/lectures. There was some great content there as well, some of which I've referenced in this lecture. For now, this is everything. Thank you again, and we hope to see you in the next lecture.